Okay, so we are going to revisit L'Hopital's rule because this is just a prerequisite into what we're going to learn after we come back later so for another week. But I thought we could go ahead and review our L'Hopital's rule this week and get this done. So L'Hopital's rule was something you learned last year, but we're going to apply it to something new this year. So we're going to include indeterminate products, differences, and powers, and I'll talk about that in just a second, okay? So what was L'Hopital's rule last year, all right? When you're evaluating a limit and you get an indeterminate form, so indeterminate forms are 0 over 0 and infinities over infinities, okay? Those are indeterminate forms. You can't evaluate or get those answers. So we had to use a special rule called L'Hopital's rule to evaluate the limit whenever you get those indeterminate forms. And I know you remember this L'Hopital's rule. L'Hopital's rule is if you're trying to find the limit of a quotient and when you plug in the number, you get 0 over 0 or infinity over infinity. The way to fix it is to take the derivative of the top function and the derivative of the bottom function and then plug in the number again and keep doing that until you're able to evaluate the limit. You just don't want to get this mixed up with the Hody-High rule, right? This is L'Hopital's rule. This is a way of evaluating a rational function and doing a limit. And it only works, L'Hopital's rule is only good if you get 0 over 0 or infinity over infinity, okay? Then you're able to apply L'Hopital's rule to see if that'll help you get your answer. And we'll review some problems here in a second. Now, the new ones that we're going to do is extending it and doing other indeterminate forms. There's something called the indeterminate product, all right, which means exactly what it says. You have a product that is not mathematically calculable, okay? You cannot do 0 times infinity. That is a product you cannot calculate, you cannot do. You also cannot do 0 times negative infinity. So you cannot multiply 0 times a number that doesn't exist, okay? That's said to be indeterminate. So we have to do the same thing with these kind of problems in order to evaluate them, okay? So here's what you do. You write the product as a quotient. So what you do is you fix it to where it's going to fit into our L'Hopital's rule that we're used to doing, all right? So you're going to rewrite the problem so that L'Hopital's rule can be applied like you're used to. So if we have a product like f times g, and this product, f times g, gives you 0 times infinity or 0 times negative infinity, then you're going to rewrite the problem. And we'll try to get that to where it goes away so it doesn't keep doing that to me. All right, we're going to rewrite the problem so that we don't have 0 times infinity. So one thing you could do is you could keep the top function as f and divide it by the reciprocal of g. So this is still f times g. It's just written in a different form. So now you would be able to work it out. Or you could do f times g. You could leave g in the numerator and do the reciprocal of f. So you're actually taking a product and writing it as a quotient by either changing function f or function g and writing it as 1 divided by the function. You're doing the reciprocal of that function. One of these forms will now put that problem into the form 0 over 0 or infinity or infinity. So you start out with having this problem, that it's a product of 0 times infinity. And then you rewrite the problem so that you either get 0 over 0 now or you get infinity over infinity now because you've now made it a fraction. Then you can use your L'Hopital's rule that you're familiar with, okay? So products you have to fix and make a quotient in order to be able to work it out. We've also got something called indeterminate differences, okay? An indeterminate difference is where you have infinity minus infinity. You cannot do infinity minus infinity. Don't ask me why. Here's my rationale. Infinity just means a really big number, but it doesn't mean they're the same. One infinity may be getting bigger faster than the other one. I know that sounds weird, but this is the way I think of it. One infinity could be like 1,000,002, and the other infinity could be 3,000,000,007. They both may not be increasing at the same rate, so they may not be the exact number at the exact same point in time. So when you subtract them, sometimes you may get a positive number. Sometimes when you subtract them a little later, they may be a negative answer. So the two infinities are not changing or approaching in the number infinity at the same rate. So the difference is not going to give you 0, if that makes sense. All right, that's the best way I can explain it. All right, so this is called an indeterminate difference, okay? So the way we fix it, there's 3 different things you can do. You can write the difference as a quotient, okay? And there's different ways to do that. You can find a common denominator. Whatever is making this affinity minus infinity, these are probably going to be fractions. So you could put them together as a common denominator. Or if it's radicals, you could do some type of rationalization type thing. Another thing you could do is factor. So it kind of depends on what's given you the infinity answer minus the infinity answer, whatever the functions are. So it depends on what the functions are that's given you infinity minus infinity. Will determine which one of these you use, whether you do a common denominator, rationalization, or you factor the problem. But what that will do is it'll make it one problem. It won't be a subtraction problem anymore. It'll now be one problem written as a quotient, especially a common denominator. Putting 2 things together using a common denominator will make it one fraction. So then once you get your quotient, we're back to 0 over 0 or infinity over infinity, and you can use your normal L'Hopital's rule. All right, you're back to the same L'Hopital's rule that you're used to. Okay. Then the last one is, it's called indeterminate powers. So there are certain powers that you cannot mathematically calculate. Like you cannot do 0 raised to the 0 power. Okay? You can't do infinity raised to the 0 power. That's not possible to do. It's not legally possible to do. You cannot do 1 to infinity, and that's the one that bothers me. 1 to infinity should still be 1, but it's not. So 1 to the infinity is because infinity keeps growing. That's the best I know how to explain that. But we can't do 1 to infinity, okay? However, this is what's freaky weird. You can do 0 to the infinity. And 0 to the infinity is 0. So go talk to a math professor and have a fun time talking about this stuff, okay? All right, just for us, we just need to memorize and know that this is possible and these are not possible. All right, so these are said to be indeterminate powers. Okay, so we can do 0 to infinity, but we can't do infinity to 0. We can't do 1 to infinity, and we can't do 0 to 0. So those are indeterminate powers. Okay, so the way to fix it, you can rewrite the function in a different way. Since these are exponents, right, we can use logarithms. Makes sense, right? So with exponents, we can always rewrite it doing logarithmic differentiation and or exponential functions with base e. So it kind of depends on the situation, whatever we're doing. Once we've written it using logarithms, you now have a product. So then you've got to take your product and write it as a fraction. So then you're going to have to do one of the product rule, the one we talked about when we had indeterminate products. All right, but once you're going to do, you're going to fix this logarithms, and then of course the power is going to multiply to the front. So then you're going to have an indeterminate product. And then once you've got the indeterminate product, then you're going to do one of the strategy for indeterminate products, which is write it as a quotient. Okay. Now, the tricky part about these is you found the natural log of something. And we're doing limits is what we're doing. You found the ln. So that means in order to actually compute the answer, you have to do this. You have to figure out the y value of the problem because you're actually trying to find the limit of y, not the limit of the ln of y. So you've got to actually calculate the limit of actually y. And that doesn't make sense until you actually look at problems. All right, so what I've talked about here, and we'll get into some examples and they'll make more sense. There are 3 kinds of things we're doing. You're used to good old L'Hopital's rule. Okay, good old L'Hopital's rule was where you got a 0 over 0 or infinity over infinity, and you were able to take the limit by doing the derivative of the numerator, the derivative of the denominator, and then plug it in again. Okay, and we're going to do plenty of examples to remind you that. What we're going to do in BC is we're going to have 3 new forms of indeterminate things going on, and we've got indeterminate products. So if it's a product, you got to make it a quotient. There's indeterminate differences. If it's a difference, you got to do some type of common denominator or something to make it a quotient. And if it's indeterminate powers, you've got to do some type of logarithmic thing to turn it into a product. And then once you get your product, you turn it into a quotient. So we just have to, it's just algebra manipulation so that you have a quotient that you can use L'Hopital's rule on. All right. So that's the content part of this. So now you watch the lesson part of it where we have the examples.